January 5, 1943. Solomon Islands, South Pacific. Lieutenant Hideo Matsumoto gripped the controls of his Mitsubishi G4M Betty bomber as he descended toward the American convoy below. He'd flown 17 missions. He knew the drill. American anti-aircraft fire was dangerous. You dodged, you weaved, you hoped the shells didn't hit you directly. But the mathematics were in his favor. At these speeds, at this altitude, the chances of a shell making direct contact with his aircraft were minuscule. Below, aboard the USS Helena, Fire Controlman 3rd Class Robert Murphy tracked the incoming bomber through his director sight. The cruiser's 5-inch gun swung smoothly, tracking the target. Murphy had done this dozens of times. You calculated the bomber's speed, altitude, and trajectory. You aimed where the aircraft would be when the shell arrived. You fired. And you hoped. But this time was different. Helena fired 3 shells. All 3 exploded near the bomber, not hitting it, but detonating within lethal distance. The Betty disintegrated. Lieutenant Matsumoto died instantly, probably never understanding what had just happened. He didn't know that Helena was carrying a new weapon, a weapon so secret that even most American sailors didn't know they had it. A weapon that would transform anti-aircraft warfare so completely that by 1945, approaching an American ship in an aircraft had become nearly suicidal. The Japanese called American anti-aircraft fire uncannily accurate. They theorized about new American radar, new American gunners, new American tactics. Some pilots claimed the Americans had developed a way to see the future. They never figured out the truth. The truth was stranger than any theory. American shells contained miniature radios. Each shell carried a complete radio transmitter and receiver no bigger than a light bulb. As the shell approached its target, the radio bounced signals off the aircraft. When the shell got within lethal distance, typically 70 feet, the radio signal triggered the fuse, detonating the shell in a shower of shrapnel that shredded anything nearby. No direct hit needed. Just get close. The Americans called it the VT fuse. VT officially stood for variable time, a deliberate cover story to hide its true nature. Radio proximity fuse was what it really was, but that name was classified higher than the Manhattan Project. The British called it the most significant military development of the war besides the atomic bomb. The Germans called it impossible. Their scientists had concluded such a device couldn't be built at reasonable cost or size. And the Japanese never figured it out at all. Even after the war ended, even after Japanese technical teams examined unexploded American shells, Japanese military intelligence never fully understood what they'd been facing. They knew American anti-aircraft fire had become devastatingly effective. They didn't know why. This is the story of the proximity fuse, the funny fuse that changed warfare. It's a story about the most sophisticated piece of mass-produced technology of World War II, about how American industry turned a laboratory curiosity into a weapon produced by the millions, and about how a device the size of a milk bottle decided the outcome of battles from the Pacific to the skies over London. This is the story of how America gave its gunners the ability to kill without aiming, and how that changed everything. To understand why the proximity fuse mattered, we need to understand the nearly impossible problem of shooting down aircraft with anti-aircraft guns. In early World War II, shooting down a fast-moving aircraft with anti-aircraft fire was extraordinarily difficult, perhaps the hardest targeting problem in military history. Consider the challenge: an aircraft is flying at 300 miles per hour, that's 440 feet per second. It might be at 15,000 feet altitude. It's maneuvering, changing course, climbing or diving. And you're trying to hit it with a shell fired from a gun on the ground, or worse, from a ship that's also moving. The shell takes time to reach altitude. During that flight time, perhaps 15 to 20 seconds, the aircraft moves over a mile. So you can't aim at where the aircraft is. You have to aim at where the aircraft will be when your shell arrives. This requires calculating the aircraft's speed, altitude, heading, and rate of climb or descent. You have to factor in wind speed and direction at various altitudes. You have to account for the shell's trajectory, which is affected by temperature, air pressure, and the Earth's rotation. And you have to do all this in seconds, while the aircraft is shooting at you. Even with the best fire control computers available in the early 1940s, this was phenomenally difficult. The standard anti-aircraft shell used a time fuse. The fuse was set before firing to explode at a specific time after leaving the gun, corresponding to when the fire control computer predicted the shell would reach the target's altitude. But this required the predictions to be perfect. If your estimate of the aircraft's altitude was off by just 500 feet, your shell would explode too early or too late, and the aircraft would fly through unharmed. The statistics were grim. In 1942, it took an average of 2,500 anti-aircraft shells to shoot down a single enemy aircraft. Some estimates put it as high as 3,000 to 4,000 shells per kill. Think about that. 3,000 shells, 3,000 individual calculations, 3,000 shells hauled up from magazines, 3,000 fuses set, 3,000 rounds loaded and fired, to bring down one aircraft. And these weren't small shells. A 5-inch anti-aircraft round weighed about 50 pounds. The larger 90mm anti-aircraft shells weighed 24 pounds each. Shooting down one aircraft might mean firing literally tons of ammunition. For the US Navy in the Pacific, this created a serious problem. Ships had limited magazine space. When under sustained air attack, as American ships frequently were in 1942 and early 1943, they could run out of ammunition. And once your magazines were empty, you were defenseless. The USS South Dakota at the Battle of Santa Cruz in October 1942 fired 1,047 5-inch rounds at attacking Japanese aircraft. She claimed 3 aircraft destroyed. That's 349 shells per kill, actually quite good by the standards of the time. But it also meant she expended nearly a third of her entire anti-aircraft ammunition load in a single battle. What would happen if the attacks continued? What if the Japanese sent more waves? Eventually, you'd run out of ammunition, and then you'd just have to sit there while Japanese bombers sank you. The Army faced similar problems. Anti-aircraft defenses around critical facilities like munitions plants, ports, and cities required enormous amounts of ammunition and still couldn't guarantee protection. During the London Blitz, British anti-aircraft batteries fired thousands of shells nightly with minimal effect. The guns were more valuable for morale, showing people that Britain was fighting back, than for actual defense. And it got worse as the war progressed. In the Pacific, Japan introduced tactics specifically designed to overwhelm anti-aircraft defenses. Multiple aircraft would attack simultaneously from different directions. Ships would have to divide their fire, reducing effectiveness further. By 1943, Japan was developing an even more deadly tactic, the kamikaze. A pilot determined to die could accept much higher levels of anti-aircraft fire than a pilot trying to survive. Traditional anti-aircraft fire needed to either destroy the aircraft completely or damage it enough to make the pilot break off the attack. Against kamikazes, only complete destruction worked. Damage wasn't enough, a burning aircraft with a dead pilot at the controls would still hit the target through sheer momentum. The Navy desperately needed a better solution. They needed a way to make anti-aircraft fire more effective without requiring perfect accuracy. They needed shells that could kill without direct hits. They needed shells smart enough to know when they were close to a target and detonate themselves at the optimal moment. They needed the proximity fuse. But building such a device seemed impossible. The concept of a proximity fuse wasn't new. Military engineers had been thinking about it since World War I. The idea was simple: put a sensor in the shell that could detect when the shell was near a target and trigger detonation automatically. No need for perfect predictions of altitude and timing. Just get the shell in the general vicinity of the aircraft, and let the shell figure out the rest. Simple concept. Impossible execution. Consider what such a device would need to do. First, it had to fit inside an artillery shell. A 5-inch naval shell is only 5 inches in diameter and about 24 inches long. Most of that space is occupied by the explosive charge and the shell casing itself. The fuse mechanism has to fit in the nose, a space perhaps the size of a large drinking glass. Second, it had to survive being fired from a gun. When an artillery shell is fired, it experiences acceleration forces of up to 20,000 times the force of gravity. That's 20,000 gs. For comparison, astronauts during rocket launches experience about 3 gs. Fighter pilots during extreme maneuvers might experience 9 gs briefly. The proximity fuse had to survive forces more than 2,000 times greater than that, and not just survive, but continue functioning perfectly. Third, it had to work reliably in the most hostile environment imaginable. Temperatures from the gun firing could exceed 5,000 degrees Fahrenheit. The shell would be spinning at up to 500 revolutions per second. Once in flight, it would experience temperatures ranging from 100+ degrees at sea level to -40 degrees at altitude. It would be subjected to wind, moisture, vibration, and extreme changes in air pressure. Fourth, it had to turn itself on after firing but not detonate until near a target. This meant it needed a safety mechanism that wouldn't activate until the shell had traveled far enough from the gun that detonation wouldn't damage the firing ship, but would activate quickly enough to be useful against aircraft. Fifth, it had to distinguish between the target and the ground or sea. Early proximity fuse concepts kept detonating when shells got close to the ocean surface, which was completely useless. The fuse had to somehow know the difference between an aircraft and the ground. Sixth, it had to be cheap enough and simple enough to mass-produce by the millions. A hand-built laboratory prototype might work, but what the military needed was millions of these devices, built by workers with limited technical training, at reasonable cost. And seventh, perhaps most difficult of all, it had to be absolutely reliable. A premature detonation could kill friendly troops. A dud that failed to detonate was wasted ammunition. In combat, reliability wasn't just desirable, it was essential. These requirements seemed contradictory. How do you build an electronic device sophisticated enough to contain a working radio transmitter and receiver, sensitive enough to detect aircraft, rugged enough to survive 20,000 gs, simple enough to mass-produce, and cheap enough to be expendable? German scientists looked at the problem and concluded it was impossible at any reasonable cost. They had scientists working on proximity fuse research, but they never developed a practical weapon. The Germans concluded that the technology required was too sophisticated for a device that would be destroyed seconds after use. British scientists came closer. They'd been working on proximity fuse research since before the war, and they had developed some promising prototypes using photoelectric cells, which would detonate when the shell's shadow passed over the target. But these were unreliable and worked only in daylight. The Americans succeeded where others failed, not because American scientists were smarter, but because American engineers were willing to try what seemed impossible, and because American industry could mass-produce sophisticated technology at a scale no other nation could match. The story begins in 1940, before America had even entered the war. In September 1940, a group of prominent British scientists arrived in Washington carrying what would later be called the most valuable cargo ever brought to our shores. The British Technical and Scientific Mission, informally known as the Tizard Mission after its leader Sir Henry Tizard, came to America with a desperate purpose: to share Britain's most closely guarded military secrets with the United States in hopes of getting American industrial help. Britain in 1940 was fighting for survival. The Battle of Britain was raging. London was being bombed nightly. Invasion seemed imminent. Britain had developed remarkable military technologies: radar, sonar, jet engines, early computer concepts, but British industry was already strained to the breaking point, just producing enough tanks, aircraft, and ammunition to continue fighting. Britain couldn't mass-produce sophisticated new weapons while simultaneously fighting Germany. But America could. America wasn't yet in the war. American industry was intact, enormous, and, critically, had the capacity to scale up production of sophisticated technology. So Britain decided to share its secrets, hoping America would help develop and produce the weapons Britain needed. The Tizard mission brought cavity magnetrons, critical for radar development, designs for jet engines, submarine detection technology, and early computer concepts. The mission is often called one of the most significant technology transfers in history. But for our story, what matters is what the Tizard mission revealed about British proximity fuse research. The British showed American scientists their photoelectric proximity fuse work and their unsuccessful experiments with radio-based fuses. American scientists were intrigued. They'd been working on similar concepts at the Naval Research Laboratory and through the National Defense Research Committee. The British information gave them new ideas. Within weeks, American scientists had formed several research teams to attack the proximity fuse problem from different angles. The lead organization was Section T, for the target, of the National Defense Research Committee, headed by Tuve at the Carnegie Institution in Washington. Tuve was a brilliant physicist who'd done pioneering work on radar. He assembled a team of top scientists and engineers and gave them a seemingly impossible mandate: develop a practical proximity fuse. Tuve's team decided early on that radio was the answer. A radio proximity fuse would emit radio waves and detect reflections bouncing back from nearby aircraft. When the reflected signal reached sufficient strength, indicating the shell was close enough, the fuse would trigger detonation. This was conceptually similar to radar, but miniaturized and ruggedized to an extreme degree. In 1940, radar sets were room-sized installations. The proximity fuse needed to fit in the nose of a shell. The team had to solve dozens of technical challenges. The tube problem: the fuse needed vacuum tubes to generate and detect radio signals. But standard radio tubes of the era were fragile glass devices that would shatter under the 20,000 G forces of gun firing. The team had to develop entirely new tube designs using techniques borrowed from light bulb manufacturing. They eventually created tubes so rugged they could be dropped on concrete floors without breaking, and that could still survive being fired from a gun. The power problem: the fuse needed a battery to power its electronics. But batteries in 1940 were bulky, heavy devices. The team developed miniature batteries using innovative designs. They also developed a generator powered by the shell's rotation. As the shell spun, a small rotor would generate electricity to supplement the battery. The safety problem: the fuse had to remain inert until the shell was safely away from the firing ship, then arm itself, then remain armed but not detonate until near a target. The team developed a mechanical safety system using centrifugal force. The spinning of the shell would gradually release safety locks as the shell traveled downrange. The discrimination problem: the fuse had to distinguish between aircraft and the ocean surface. Early prototypes detonated when shells descended close to the water, which was useless for anti-aircraft work. The team eventually solved this by carefully tuning the radio frequency and signal processing, though the exact details remained classified for decades. The reliability problem: every component had to be absolutely reliable. A single failed tube, a loose wire, a weak solder joint, any failure meant a dud shell. The team developed extensive quality control procedures and tested components to destruction to ensure reliability. By late 1941, they had a working prototype. It was crude, expensive, and required hand assembly by skilled technicians. But it worked. In January 1942, the Navy conducted secret tests at sea. A radio-controlled drone aircraft flew patterns at various altitudes and ranges. Ships fired proximity-fused shells. The results were stunning. Shells that would have missed with conventional fuses detonated near the drone, shredding it with shrapnel. The hit rate was approximately 5 to 7 times better than with conventional time-fused shells. The admirals watching the tests immediately grasped the implications. This weapon could transform naval anti-aircraft defense. They wanted it in production immediately. But there was a problem: each prototype fuse cost about $1,000 to build, equivalent to about $18,000 today, and required hours of hand assembly by skilled technicians. The Navy needed millions of these devices. At prototype costs and production rates, equipping the fleet would be impossible. The proximity fuse had been proven in the laboratory. Now came the harder part: mass production. In spring 1942, the proximity fuse program faced its greatest challenge: transforming a hand-built laboratory device into a mass-produced weapon. The National Defense Research Committee contracted with multiple American companies to develop production methods. The lead contractors were Western Electric, the manufacturing arm of AT&T, Raytheon Manufacturing Company, Sylvania Electric Products. Eastman Kodak, for specialized components. Crossley Corporation, a radio manufacturer. Each company brought different expertise. Western Electric had experience mass-producing telephone equipment, technology requiring reliability and precision assembly. Raytheon specialized in radio tubes. Sylvania made electric components. Together, they had to figure out how to build proximity fuses not one at a time in laboratories, but by the thousands per day in factories. The challenges were enormous. Consider just one component, the vacuum tubes. The original prototypes used 4 different specialized tubes. Each tube had to be tested individually, assembled into the fuse, then the entire fuse had to be tested. The labor requirements were staggering. Engineers redesigned the tubes for easier manufacturing. They developed automated testing equipment that could test hundreds of tubes per hour. They created assembly jigs that allowed less skilled workers to assemble tubes consistently. But tubes were just one component. The fuse contained dozens of parts: resistors, capacitors, batteries, wiring, the radio frequency generator, the detector circuit, the firing mechanism, the safety system, the generator powered by shell rotation. Each part had to be miniaturized, ruggedized, and designed for mass production. Western Electric took the lead in redesigning the entire fuse for manufacturability. Their engineers, experienced with telephone equipment production, applied assembly line principles to proximity fuse manufacturing. They created specialized machinery for nearly every production step. Machines to wind wire coils. Machines to assemble tube elements. Machines to solder connections. Machines to test components. Machines to test complete fuses. They developed idiot-proof assembly procedures so that workers with minimal training could assemble fuses correctly. Each workstation had pictures showing exactly what the worker should do. Pass-fail criteria were obvious: if a part fit, it was correct; if it didn't fit, it was wrong. They implemented quality control procedures borrowed from both telephone manufacturing and munitions production. Every fuse was tested multiple times during production. Random samples underwent destructive testing, fired from a gun at a test range to verify they worked after experiencing gun firing forces. Production began slowly in late 1942. The first fuses were expensive, about $740 each, still equivalent to over $13,000 today. But as production ramped up and procedures improved, costs fell rapidly. By early 1943, fuse production reached about 40,000 units per month, at a cost of about $20 per fuse, equivalent to about $350 today. By mid-1944, monthly production exceeded 1 million fuses, and costs had fallen to about $18 per fuse. By war's end, American industry had produced approximately 22 million proximity fuses at a total program cost of about $1 billion in 1940s dollars, roughly $17 billion today. To put that in perspective, the Manhattan Project, which developed the atomic bomb, cost about $2 billion. The proximity fuse program cost half as much as the atomic bomb, and arguably had greater immediate military impact. But producing the fuses was only part of the challenge. The program also had to maintain absolute secrecy. The proximity fuse was one of the most closely guarded secrets of World War II, arguably more closely guarded than the Manhattan Project in its early years. The reason for the secrecy was simple: if the enemy captured an intact proximity fuse and reverse-engineered it, they could develop their own version. Or worse, they could develop countermeasures, jamming signals or decoys that would cause premature detonation. Most devastating, if the enemy understood the principle, they would change tactics to minimize its effectiveness. The security program around the proximity fuse was elaborate and paranoid, necessarily so. First, even the name was classified. The official designation was a VT fuse, with VT supposedly standing for variable time, suggesting it was just an improved mechanical time fuse. This cover story was maintained throughout the war. Even many American military personnel didn't know what VT really meant. The actual design details were classified at levels higher than most atomic bomb information. Fewer than 1,000 people in America knew the complete design. Factory workers who assembled fuses were told they were making radio components for unspecified military use. They weren't told these were proximity fuses or how they worked. Second, strict rules governed when and where the fuses could be used. Initially, through most of 1943, the Navy prohibited using proximity fuses over land because a dud fuse falling on enemy territory might be recovered and analyzed. They could only be used over water, where duds would sink beyond recovery. When proximity fuses were first used operationally in January 1943, gun crews were given special orders, never acknowledge that these are anything unusual. If asked, they're just new time fuses. Don't discuss their effectiveness. Don't write about them in letters home. Don't talk about them even with other sailors who aren't on gun crews. Third, elaborate procedures protected the fuses themselves. On Navy ships, proximity-fused ammunition was stored separately from other ammunition, in special magazines with additional security. Before loading, each fuse was checked to verify its safety mechanisms were intact, preventing premature detonation if the ship was hit. The fuses themselves had anti-tampering features. If someone tried to open a fuse without proper tools and procedures, it would destroy its internal components. This meant that even if the Japanese captured a fuse, they might destroy it while trying to examine it. Fourth, the military implemented strict salvage procedures. If a proximity-fused shell was fired but didn't detonate, either because it missed and fell into the ocean, or because the fuse failed, crews were instructed to record its approximate location. Later, if feasible, salvage teams would attempt recovery. The military was desperate to prevent enemy recovery of intact fuses. These precautions seemed extreme, but they worked. Despite millions of proximity-fused shells being fired during the war, Germany and Japan never successfully reverse-engineered the technology. The Germans eventually captured some proximity fuses from shells that fell on land during the Battle of the Bulge in December 1944. German scientists examined them and determined they contained miniature radios. But by then it was too late. Germany lacked the industrial capacity to manufacture their own version, and the war would be over before they could develop countermeasures. Japan apparently never captured an intact fuse. Japanese technical intelligence documented the extreme effectiveness of American anti-aircraft fire but never determined why. Japanese reports speculated about new radar, new fire control computers, or new American training methods. They never figured out that the shells themselves were intelligent. Even after the war, when American technical teams interviewed Japanese military officers and scientists, the Japanese were shocked to learn about proximity fuses. They had known American anti-aircraft fire was extraordinarily effective. They had developed theories and tactics to try to counter it. But they'd been fighting blind, never understanding the real nature of the weapon killing their pilots. This intelligence failure had enormous consequences. The proximity fuse was first used operationally on January 5, 1943, the opening scene of our story, when USS Helena fired 3 shells and destroyed a Japanese bomber with all 3 exploding near the target. That first combat use was carefully planned. Helena was operating near Guadalcanal in the Solomon Islands, waters firmly controlled by the U.S. Navy, ensuring any dud shells would fall into deep ocean where they couldn't be recovered by Japan. The cruiser's gun crews had been specially trained. They'd been told these were new experimental fuses and given instructions on handling and firing procedures. They hadn't been told exactly how the fuses worked. Most gun crews assumed they were just improved time fuses. When the Japanese bomber approached, Helena's fire control radar tracked it. The gun director calculated a firing solution. 3 shells fired. And all 3 detonated near the aircraft without direct hits, shredding it with shrapnel fragments traveling at thousands of feet per second. The bomber disintegrated. The crew probably died instantly, never knowing what had killed them, only that suddenly their aircraft was being torn apart by explosions that seemed impossibly accurate. For the American gun crews, it seemed almost miraculous. Shooting down aircraft with anti-aircraft guns was normally frustrating work. You fired dozens of shells and watched them explode harmlessly while the target flew past. But this? This was different. This was like having a weapon that couldn't miss. Over the following weeks, as more proximity fuses reached the fleet, American anti-aircraft effectiveness increased dramatically. Statistics tell the story. In 1942, before proximity fuses, Navy records showed it took an average of 2,500 anti-aircraft shells to shoot down one attacking aircraft. By mid-1943, after proximity fuses entered service, it took an average of 250 shells per kill, a tenfold improvement. But raw numbers don't capture the psychological impact. Japanese pilots began reporting that American anti-aircraft fire had become uncannily accurate. Pilots who'd survived previous attacks returned shaken, describing shells that seemed to know where they were, that exploded without hitting the aircraft but still caused catastrophic damage. Japanese tactical commanders noticed the change. In previous battles, they could accept certain loss rates during attacks, perhaps 10 to 20% losses were acceptable if the attack succeeded. But now losses were spiking to 40 to 50% or higher. Attacks that would have succeeded in 1942 were being shredded before reaching targets. Let me describe several key battles where proximity fuses proved decisive. The Battle of Rennell Island, January 29 to 30, 1943. Japanese naval bombers attacked an American cruiser force. The Japanese had planned their attack well, using night conditions and coming in at varying altitudes to make anti-aircraft fire less effective. But the American ships were equipped with proximity fuses and radar fire control. As Japanese bombers began their attack runs, American 5-inch guns opened fire. Multiple bombers disintegrated before they could release torpedoes. Survivors reported shells exploding impossibly close, filling the air with shrapnel. The attack degenerated into chaos, with pilots breaking formation to avoid the apparently guided explosions. The heavy cruiser USS Chicago was hit by torpedoes and later sank, but Japanese losses were catastrophic, 14 bombers shot down out of 31 attacking aircraft, a loss rate of 45%. For comparison, in similar attacks in 1942, Japanese losses averaged 10 to 15%. The Japanese Navy was shocked by the losses. They knew something had changed in American defensive capabilities. They didn't know what. The Battle of the Philippine Sea, June 19 to 20, 1944. Also called the Great Marianas Turkey Shoot, this battle saw massive Japanese air attacks on American carrier forces and massive Japanese losses. American carriers were equipped with both proximity-fused 5-inch anti-aircraft guns and proximity-fused 40mm and 3-inch guns. The result was a defensive firepower umbrella that Japanese aircraft couldn't penetrate. Of approximately 373 Japanese aircraft that attacked the American carriers, about 330 were shot down. The Americans lost 29 aircraft. It was the most lopsided air battle in naval history. Proximity fuses didn't deserve sole credit. American fighter aircraft, radar early warning, and superior tactics all contributed. But American anti-aircraft gunners firing proximity-fused ammunition destroyed many Japanese aircraft that broke through the fighter screen. Japanese pilots reported flying through walls of explosions. One surviving pilot described it as like flying through a thunderstorm made of shrapnel. Another said American ships seemed to have invisible barriers around them that destroyed aircraft. The Battle of the Philippine Sea essentially destroyed Japanese naval aviation as an effective force. After this battle, Japan lacked the trained pilots and aircraft to seriously threaten American carriers. The proximity fuse had contributed to ending Japanese hopes of victory through carrier warfare. Kamikazes and Okinawa, April-June 1945. By 1945, Japan had largely abandoned conventional bombing attacks in favor of kamikaze suicide attacks. The logic was brutal but pragmatic: if attacking American ships meant near-certain death anyway, because American anti-aircraft fire was so effective, might as well make that death count by turning the aircraft itself into a weapon. The kamikaze tactic was specifically designed to counter American defensive advantages. A kamikaze pilot didn't need to survive long enough to line up a bombing run and escape. He just needed to get close enough to crash into the target. Damage to the aircraft didn't matter. A burning plane with a dead pilot at the controls was still a deadly weapon through sheer momentum and explosive payload. This should have made American proximity fuses less effective. After all, they worked by damaging aircraft at range, but damage wasn't enough against kamikazes. But proximity fuses still proved devastatingly effective against kamikazes if used at maximum effectiveness. The key was volume of fire and range. Proximity fuses allowed American ships to open fire at extreme range, up to 10 miles out, and have reasonable probability of damaging attacking aircraft. Multiple damaged aircraft would lose control, crash into the sea short of targets, or be knocked off course enough that they missed. At Okinawa, American ships faced the largest kamikaze attacks of the war, over 1,900 kamikaze sorties attacking the invasion fleet over 3 months. American losses were significant: 36 ships sunk, 368 damaged, about 4,900 sailors killed. But Japanese losses were catastrophic. Of those 1,900 kamikaze sorties, about 14% successfully hit ships. The rest were shot down or missed. Given that each kamikaze aircraft carried a pilot with months or years of training, this was an exchange ratio Japan couldn't sustain. The proximity fuse didn't make ships invulnerable to kamikazes, but it made kamikazes far less effective than they would have been otherwise. Japanese commanders after the war noted that kamikaze tactics were partly driven by the impossibility of conventional bombing attacks. One admiral stated, "When it became apparent that our aircraft could rarely penetrate American defenses to reach bombing positions, the decision to employ special attack, kamikaze, tactics became logical." In other words, American anti-aircraft effectiveness, substantially enhanced by proximity fuses, made conventional tactics suicidal, so Japan adopted tactics that were literally suicidal. Proximity fuses were initially restricted to Pacific naval use because of security concerns. Any fuse falling on land might be recovered by the enemy. But by late 1944, 2 factors changed this calculation. First, Allied forces were clearly winning the war. Even if Germany captured and reverse-engineered proximity fuses, they lacked time and industrial capacity to produce their own version or develop effective countermeasures before the war ended. Second, Germany had introduced a new weapon where proximity fuses could be decisive: the VE-1 flying bomb. The VE-1 was a cruise missile before the term existed, an unmanned aircraft packed with explosives that flew on autopilot toward London and other targets. Germany launched thousands of them starting in June 1944. The VE-1 was terrifying for civilians but actually made an ideal target for proximity fuses. Unlike manned aircraft, V-1s flew straight and level at constant altitude and speed. They didn't dodge or maneuver. This made them much easier targets, if you could hit them. But hitting a small, fast-moving target was still difficult with conventional anti-aircraft fire. In the first weeks of V-1 attacks, British anti-aircraft batteries and fighters together shot down only about 24% of incoming V-1s. The rest hit London, causing casualties and damage. In July 1944, British anti-aircraft defences around London began receiving proximity-fused ammunition from American stocks. The Americans had been reluctant to share this technology even with their closest ally, but the V-1 threat was serious enough to justify the risk. The results were immediate and dramatic. In the first week using proximity fuses, early July 1944, British anti-aircraft batteries shot down about 24% of V-1s that reached the gun belt around London. By the second week, 46% shot down. By the third week, 67% shot down. By the fourth week, 79% shot down. Think about that progression. In 1 month, kill rate more than tripled, from 1 in 4 to 4 in 5. What happened? The proximity fuses allowed anti-aircraft guns to destroy V-1s without direct hits. Shells that exploded within 70 feet of a V-1 would shred its thin aluminum skin and destroy its guidance system or fuel tank. The V-1 would crash harmlessly in open areas short of London. British anti-aircraft commanders were ecstatic. After months of frustration fighting the V-1 threat, they finally had an effective defense. By August 1944, between anti-aircraft guns, using proximity fuses, and fighter aircraft, Britain was destroying over 80% of V-1s before they reached London. This essentially ended the V-1 as an effective weapon. Germany continued launching them, but losses were so high that the strategic impact was negligible. Proximity fuses also saw use in land combat in Europe, but in a different role, artillery. In December 1944, during the Battle of the Bulge, American artillery units received proximity fuses for use with field artillery shells. These weren't for anti-aircraft use, they were for use against ground targets. A proximity-fused artillery shell would detonate about 10 to 30 feet above the ground, showering the area below with shrapnel. This airburst effect was much more deadly against infantry than conventional shells that exploded on impact with the ground, where much of the blast and shrapnel was absorbed by terrain. American artillery using proximity fuses devastated German infantry attacks during the Battle of the Bulge. German soldiers reported that American artillery seemed impossibly accurate and deadly. Shells would explode in the air above them, making trenches and foxholes useless for protection. Some German commanders reported entire companies, 100 to 150 men, being destroyed by just a few artillery barrages using these new shells. The psychological impact was as significant as the physical impact. German troops became reluctant to advance when they knew American artillery might hit them with airbursting shells. It was during the Battle of the Bulge that Germany finally captured some intact proximity fuses from shells that didn't detonate. German scientists quickly examined them and realized they contained miniature radios. A captured German report from January 1945 stated, "The Americans have developed artillery shells with miniature radio fuses that detonate near targets without direct hits. The technology required is remarkable. We estimate these fuses contain transmitters and receivers smaller than any we have manufactured. The manufacturing implications are staggering. Mass production of such sophisticated devices indicates American industrial capacity beyond our previous estimates." But this discovery came too late. Germany was collapsing. Even if German scientists could design their own proximity fuses, German industry could no longer mass-produce sophisticated electronics. And the war would be over before countermeasures could be developed and deployed. Let's talk about what the proximity fuse program actually cost and what America produced. Total program cost, approximately $1 billion in 1940s dollars, equivalent to roughly $17 billion today. That covered all research and development, building specialized production facilities, manufacturing 22 million proximity fuses, quality control and testing, training programs, security measures. For comparison, the Manhattan Project, atomic bomb $2 billion, 1940s dollars. The entire B-29 bomber program, $3 billion. The Liberty ship program, $13 billion. The proximity fuse cost half as much as developing the atomic bomb, delivered 3 years earlier, and had arguably greater immediate military impact. Production numbers are staggering. Total proximity fuses manufactured, approximately 22 million units. By type: 5-inch naval anti-aircraft, 12 million fuses. 90 mm Army anti-aircraft, 5 million fuses. 40 mm anti-aircraft, 3 million fuses. 105 mm field artillery, 2 million fuses. Peak production, over 1.5 million fuses per month by mid-1945. These weren't simple devices. Each fuse contained 4 to 5 miniature vacuum tubes, approximately 100 other components, resistors, capacitors, wires, etc. A battery system, a mechanical generator, safety mechanisms, the firing mechanism itself. Every component had to be tested. Every fuse had to be tested multiple times. Random samples were fired from guns to verify they worked after experiencing 20,000 G-forces. The industrial effort was massive. At peak production, about 10,000 workers directly employed in fuse manufacturing. About 50,000 workers producing components for fuses. Hundreds of engineers continuously improving designs and production methods. Thousands of military personnel in training, logistics, and quality control. And yet the cost per fuse fell dramatically through the war. Early 1943, $7.40 per fuse. Late 1943, $35 per fuse. Mid-1944, $22 per fuse. Late 1944, $18 per fuse. This cost reduction, from $740 to $18, came from design improvements making manufacturing easier, better production equipment, economy of scale, learning curve effects as workers became more skilled. Even at $18 per fuse, about $315 in today's money, this was expensive ammunition. A conventional time fuse cost about $2. So proximity fuses cost about 9 times more than conventional fuses. But they were 5 to 7 times more effective. The math worked. Paying 9 times more for ammunition that was 5 to 7 times more effective was a bargain. Plus, you needed far less ammunition to achieve the same result, which saved on logistics. Ships could carry less ammunition and still maintain longer effective combat capability. The Navy calculated that proximity fuses saved lives. If conventional fuses required 2,500 shells to shoot down an aircraft, and proximity fuses required only 250 shells, then ships could defend themselves 10 times longer before exhausting their magazines. That meant fewer ships sunk by aircraft that attacked after the ship's ammunition was exhausted. The program also accelerated technology development in areas that would become important post-war. Miniaturization of electronics, ruggedized component design, quality control for mass-produced electronics, automated testing procedures. Many engineers who worked on proximity fuses went on to careers in post-war electronics industry, bringing expertise in miniaturization and reliability. Some historians argue the proximity fuse program helped enable America's post-war electronics industry boom. What did the Japanese actually know about proximity fuses during the war? And what did they learn after the war? The answer is, remarkably little, and they were shocked when they found out. During the war, Japanese naval intelligence documented the increasing effectiveness of American anti-aircraft fire. Reports from late 1942 onward noted that American ships seemed to be achieving hit rates that shouldn't be possible with conventional time-fused ammunition. A Japanese Navy intelligence assessment from March 1943 stated, American anti-aircraft fire has become significantly more effective since January. Observed hit rates suggest accuracy improvements of 5 to 1 or greater compared to previous engagements. Possible explanations: 1. New American radar fire control systems. 2. Improved training of gunners. 3. New ammunition or fuses, for a statistical anomaly. Recommend continued observation and analysis. If pattern persists, we must adjust attack tactics accordingly. Note that new ammunition or fuses was listed as a possibility, but it was third on the list and wasn't considered the most likely explanation. By mid-1943, Japanese naval air commanders were reporting that attacking American ships had become dramatically more dangerous. Loss rates in attacks on carrier groups had increased to 40 to 50% compared to 15 to 20% in early 1942. Japanese tactical intelligence tried to develop countermeasures based on what they could observe. They recommended attacks at night, assuming American accuracy advantage came from visual fire control. It didn't. Radar fire control worked fine at night. They recommended varying altitude and approach angles to confuse fire control systems. This helped slightly but couldn't overcome the proximity fuse advantage. They recommended faster approach speeds. This actually made things worse. Faster aircraft covered less distance in evasive maneuvers, giving proximity fuses more chances to score near misses. None of these countermeasures addressed the actual problem because the Japanese didn't understand what the actual problem was. By late 1944, Japanese intelligence was reporting that American anti-aircraft fire seemed to have some kind of influence mechanism, shells that exploded near aircraft without apparently hitting them. But they couldn't determine the mechanism. Some Japanese analysts theorized about directed energy weapons. Others suggested proximity detecting mechanisms but concluded these would be impossibly sophisticated to mass produce. The prevailing theory remained that Americans had achieved dramatic improvements in radar fire control. The kamikazes were partly a response to this defensive effectiveness. If conventional attacks were being destroyed at 40 to 50% rates before reaching targets, kamikaze attacks at least guaranteed that casualties resulted in damage. A destroyed kamikaze aircraft could still crash into the target through momentum. But even kamikaze tactics struggled against proximity fuses. American ships could open fire at extreme range, 8 to 10 miles, and achieve hits. A kamikaze aircraft damaged at 8 miles might still be under control, but might be trailing smoke, losing altitude, handling poorly. By the time it reached its target, if it reached its target, it was struggling to maintain heading and might miss. Japanese commanders noted this but attributed it to multiple factors: radar fire control, volume of fire, radar-directed fighters, without understanding that the shells themselves were intelligent. After the war ended, American technical intelligence teams interviewed Japanese military officers and scientists as part of understanding Japanese military capabilities. During these interviews, Americans asked about Japanese knowledge of proximity fuses. The Japanese officers were confused. They asked what a proximity fuse was. When Americans explained, the Japanese were shocked. Multiple accounts describe Japanese naval officers expressing disbelief, then understanding, then a kind of resigned admiration. One Japanese admiral stated, "So that's what it was. We knew your anti-aircraft fire had become impossibly effective. We developed theories, better radar, better training, better tactics. We never imagined you'd put radios inside every shell. The industrial capacity required, it's hard to comprehend." A Japanese scientist on the technical team that examined American equipment after the war said, "When we opened the proximity fuse and saw what was inside, miniature tubes, the radio components, all designed to survive gun firing and function perfectly, we realized we'd been fighting an enemy with industrial and technical capabilities far beyond our own. We couldn't have manufactured such devices in those quantities even if we'd understood the principle." The Japanese had been fighting blind against a weapon they never understood. Post-war analysis by Japanese military historians suggested that proximity fuses might have extended the war in certain ways. By making conventional bombing attacks nearly suicidal, proximity fuses, along with other defensive improvements, forced Japan to adopt kamikaze tactics. Kamikazes, while still suffering heavy losses, were more effective than conventional attacks would have been. In other words, without proximity fuses, conventional Japanese bombing attacks might have continued but with lower effectiveness and lower casualties. With proximity fuses, Japan was forced to adopt kamikaze tactics, which were horrific but achieved better damage-to-casualty ratios than conventional attacks would have against proximity fuse-equipped ships. This is a grim calculus, but it illustrates how the weapon changed Japanese strategy. The proximity fuse didn't end with World War II. It transformed warfare permanently. Immediate post-war impact. In August 1945, after Japan surrendered, the proximity fuse program was declassified. For the first time, the public learned about the VT fuse and what it really was. The revelation was sensational. Newspaper headlines declared it the weapon that won the war and the shell that thinks. Popular Science and Popular Mechanics ran detailed articles explaining the technology. The proximity fuse captured public imagination as a symbol of American technical and industrial superiority. Scientists and engineers who'd worked on the program could finally talk about what they'd done. Many published academic papers on the technical challenges they'd overcome. The miniaturization techniques, reliability engineering methods, and quality control procedures developed for proximity fuses influenced post-war electronics industry development. The Korean War. The proximity fuse proved critical again in the Korean War, 1950 to 1953. American and UN forces used proximity-fused ammunition extensively for both anti-aircraft and artillery purposes. Against North Korean and Chinese aircraft, proximity fuses maintained their effectiveness. Against ground targets, proximity-fused artillery provided devastatingly effective firepower. One notable engagement, in November 1950, Chinese forces launched massive human wave attacks against American positions. American artillery using proximity-fused shells devastated these attacks. Shells detonating 20 to 30 feet above the ground showered attacking infantry with shrapnel. Traditional trenches and foxholes provided little protection. American commanders credited proximity-fused artillery with breaking several major Chinese offensives that might otherwise have overrun defensive positions. The Cold War. During the Cold War, proximity fuses became standard for all American anti-aircraft weapons and most artillery shells. Every NATO nation adopted them. The Soviet Union developed their own versions. They'd obtained examples from captured German stocks in 1945. The technology evolved. Radar proximity fuses became smaller and more reliable. Laser proximity fuses, using laser ranging instead of radio, were developed for certain applications. Infrared proximity fuses, detecting heat signatures, were developed for missile applications. Digital signal processing improved discrimination between real targets and false returns. By the 1960s, virtually every surface-to-air missile used some form of proximity fuse. The idea that a missile needed to directly hit its target was obsolete. Missiles just needed to get close. Modern warfare. Today, proximity fusing is ubiquitous in military applications. Air-to-air missiles nearly all use proximity fuses, detonating near the target to damage it with expanding rod warheads or fragmentation. Surface-to-air missiles all use proximity fuses. Anti-aircraft artillery all use proximity-fused ammunition. Artillery shells, many modern shells can be set for airburst, proximity, or impact detonation depending on the target. Naval guns, all major caliber naval guns have proximity-fused ammunition available. The principle has also extended to non-military applications. Airbag sensors in cars work on similar principles, detecting proximity to obstacles. Automated manufacturing uses proximity sensors throughout. Smartphone touchscreens use capacitive proximity sensing. The historical perspective. Military historians generally rank the proximity fuse as one of the most significant weapon developments of World War II, alongside radar, the atomic bomb, and the aircraft carrier. Unlike the atomic bomb, used twice, or the aircraft carrier, expensive and requiring years to build, the proximity fuse was mass-producible, usable in vast quantities, and provided immediate tactical benefit every time it was used. Some argue it was more important than the atomic bomb in actual military impact during World War II. The proximity fuse contributed to winning battles from 1943 onward, while the atomic bombs were used only at the very end of the war. The British scientist and historian R.V. Jones called it one of the three most valuable of all the myriad radio and radar devices in the war, the other two being radar itself and RDF, radio direction finding. Winston Churchill mentioned it in his memoirs. The proximity fuse was one of the most brilliant of American wartime developments, and it came at a critical time. Admiral Ernest King, Chief of Naval Operations during the war, wrote, "The proximity fuse was a transformative weapon. It made anti-aircraft defense actually effective instead of merely hopeful. I believe it saved hundreds of ships and thousands of lives." The engineering triumph. Perhaps the most remarkable aspect of the proximity fuse program was the engineering achievement of making it work at scale. The prototype fuses demonstrated in early 1942 proved the concept was possible. But making 22 million units that worked reliably under combat conditions, at a price the military could afford, manufactured by workers with limited technical training, that was the real achievement. This required innovations in miniaturization, cramming sophisticated electronics into tiny spaces. Ruggedization, making delicate electronics survive 20,000 G shocks. Reliability engineering, ensuring components work despite hostile environments. Quality control, testing millions of units effectively. Manufacturing engineering, designing production processes for complex devices. Supply chain management, coordinating hundreds of suppliers. These innovations influenced post-war American industry. Engineers who learned these techniques on proximity fuses applied them to commercial electronics, telecommunications, computers, and other fields. The proximity fuse program demonstrated that sophisticated technology could be mass-produced at scale, a lesson that shaped America's approach to technology development throughout the Cold War and beyond. Before we conclude, let's talk about some of the people behind the proximity fuse who deserve recognition. Moltke, 1901 to 1982. Tuve was the director of Section T of the National Defense Research Committee, the group that developed the proximity fuse. He was a physicist who'd done pioneering work on radio waves and radar before the war. Tuve assembled the team, organized the research effort, and drove the program forward despite enormous technical challenges. He worked closely with military leaders to understand requirements and with industry to solve manufacturing challenges. After the war, Tuve received relatively little public recognition because the proximity fuse program remained classified until 1945. But within the scientific and military communities, he was regarded as one of the unsung heroes of the war. Tuve went on to do important work in radio astronomy and geophysics. He died in 1982. Richard B. Roberts. Roberts was the physicist who led the team that actually designed the radio proximity fuse mechanism. He solved many of the critical technical problems: how to make tubes rugged enough to survive gun firing, how to process the radar return signal reliably, how to power the device. Roberts worked at the Carnegie Institution's Department of Terrestrial Magnetism under Tuve. He was brilliant at practical problem solving, turning theoretical concepts into working hardware. After the war, Roberts continued work in defense electronics and helped develop early missile guidance systems. He died in 1980, having received various honors from scientific organizations but little public recognition. Lawrence Hafstad. Hafstad was another key physicist on Tuve's team. He worked on the power systems for the fuse, developing the miniature batteries and the mechanical generator that charged them using the shell's rotation. After the war, Hafstad became a leader in nuclear reactor development and helped establish the Atomic Energy Commission's reactor programs. Harry Diamond, 1900 to 1948. Diamond led the parallel Army effort to develop proximity fuses at the Army's Diamond Ordnance Fuse Laboratory, later renamed the Harry Diamond Laboratory in his honor after his death. The Army's effort focused on fuses for artillery shells and anti-aircraft guns, while the Navy's effort focused on naval guns. The two programs coordinated but had different technical requirements. Diamond made key contributions to reliability engineering and quality control procedures that ensured fuses worked under field conditions. The industrial teams. Thousands of engineers at Western Electric, Raytheon, Sylvania, and other companies solved the manufacturing challenges that made mass production possible. At Western Electric, a team led by M.J. Kelly developed the automated production equipment and assembly procedures that brought costs down from $740 per fuse to $18 per fuse. At Raytheon, engineers developed new vacuum tube designs that could be manufactured by the millions. At Sylvania, teams developed testing equipment that could verify fuse function without firing them. These engineers received even less recognition than the scientists, but their contributions were equally essential. The proximity fuse only mattered because it could be mass-produced. The workers. Finally, tens of thousands of factory workers, many of them women, assembled the proximity fuses that won battles. These workers often didn't know what they were building. They were told they were making radio components for military use without being told these were smart fuses for anti-aircraft shells. They worked in facilities with strict security. They followed precise assembly procedures. They took pride in their work even without knowing its full purpose. After the war, many of these workers learned what they'd actually been making. There are accounts of women who worked in proximity fuse factories describing their pride when they realized the devices they'd assembled had saved ships and lives. These workers were part of the arsenal of democracy, the American industrial workforce that turned America's manufacturing capacity into military advantage. Let's return to where we started, January 5, 1943, when USS Helena fired 3 shells at a Japanese bomber and all 3 exploded near the target without direct hits. Lieutenant Hideo Matsumoto died that day, never knowing what killed him. He probably had time to see the explosions around his aircraft, 3 blossoms of fire and shrapnel appearing impossibly close in rapid succession. Then his aircraft was tearing apart and he was falling toward the ocean below. He didn't know he'd just become one of the first combat casualties of a new weapon, one that would transform warfare and help decide the outcome of the Pacific War. Over the following months and years, tens of thousands of other Japanese pilots, sailors, and soldiers would die from proximity-fused weapons. most would die as confused as Lieutenant Matsumoto, never understanding why American anti-aircraft fire had become so devastatingly effective. The proximity fuse worked because it solved an impossible problem: how to shoot down fast-moving aircraft with artillery. Traditional anti-aircraft fire required perfect prediction. You had to calculate exactly where the aircraft would be seconds in the future and fire a shell to that exact position. Miss by 100 feet and the shell exploded harmlessly. The proximity fuse changed the equation. You didn't need perfection. You just needed to get close, within 70 feet, and the shell would detonate itself at the optimal moment. This transformed anti-aircraft fire from a game of precision to a game of probability, and the probabilities shifted dramatically in favor of defense. This is why the Japanese never figured it out. From their perspective, American gunners had just gotten impossibly good at predictions. They theorized about better radar, better training, better fire control computers. They never imagined that the shells themselves were intelligent. The industrial achievement was as remarkable as the scientific achievement. American industry produced 22 million sophisticated electronic devices, each containing miniature radios and designed to survive conditions that would destroy any normal electronic device, at costs that declined from $740 to $18 per unit. No other nation could have done this. Germany had the scientific capability but lacked the industrial capacity. Their economy was already strained producing conventional weapons. Japan had neither the scientific understanding nor the industrial capability. Only America, with its vast industrial base untouched by bombing, its skilled workforce, and its tradition of mass production, could turn a laboratory curiosity into a weapon produced by the millions. The proximity fuse demonstrated something profound about how wars are won. They're not won just by brave soldiers and clever tactics. They're won by nations that can mobilize science, engineering, and industry to create weapons their enemies cannot match. For words changed the Pacific War, short on fresh water. Those were the fake words that proved to Admiral Nimitz that the Japanese target was Midway, allowing him to position his carriers to ambush the Japanese fleet. But for other words changed the nature of warfare: no direct hit needed. That was the promise of the proximity fuse. And it was a promise America delivered on 22 million times. When Lieutenant Matsumoto's bomber disintegrated over the Solomon Islands on January 5, 1943, it marked the beginning of a new era in warfare. An era where defense could match offense. An era where approaching a defended position meant flying through a storm of shells that didn't need to hit you to kill you. The proximity fuse didn't win World War II by itself. But it contributed significantly to victory, saving ships, lives, and time. It made America's anti-aircraft defenses actually effective. It made Japanese air attacks increasingly futile. It helped American ships survive in hostile waters. It destroyed V-1 rockets over London. It devastated infantry attacks in Europe and Korea. And it taught both America and its enemies a lesson: technical and industrial superiority matters. The nation that can innovate faster, produce smarter weapons, and manufacture them at scale has an enormous advantage. Japan learned this lesson too late. By the time they understood what they were facing, they'd already lost. Their pilots kept dying in attacks that seemed impossible to survive. Their generals kept wondering why American defenses had become so effective. Their scientists kept trying to explain what they didn't understand. And somewhere in a basement in Pearl Harbor, Commander Joseph Rochefort, who'd used a different kind of intelligence trick with his fake water shortage message at Midway, might have appreciated the irony. Both sides were using deception and technology to gain advantages their enemies couldn't understand. But only one side could turn those advantages into weapons produced by the millions and deployed throughout its forces. The proximity fuse was many things: a scientific triumph, an engineering achievement, an industrial marvel, and a military game-changer. But perhaps most importantly, it was proof that in modern warfare, the nation that can innovate and produce at scale has an advantage no amount of bravery or tactical skill can overcome. Lieutenant Matsumoto died not knowing what killed him. Tens of thousands of others died the same way over the following years, killed by a weapon they never understood, fired from ships they couldn't effectively attack anymore. The funny fuse that made Japanese pilots ask how are they hitting us changed warfare forever. And Japan never figured out the answer. Epilogue: the question Japan never answered. After the war, American technical intelligence teams visited Japan to interview military and scientific personnel. One recurring theme in these interviews was Japanese confusion about American anti-aircraft effectiveness. A Japanese naval commander, when shown a proximity fuse for the first time after the war ended, held it in his hands for several minutes without speaking. Finally he said, "This is what killed so many of our pilots? This small device." When the American officer confirmed this, the Japanese commander continued, "We knew something had changed. We developed theories. We changed tactics. We trained our pilots to expect very heavy anti-aircraft fire. We told them American ships could track them perfectly with radar. We told them American gunners were very well trained. We told them to expect casualties of 40 or 50% on attacks. But we never imagined this. A radio in every shell? Millions of them? The industrial capacity, the technical sophistication, we couldn't have imagined it. We thought we were fighting an enemy with better radar and better gunners. Instead, we were fighting an enemy with a completely different technology. An enemy who could afford to put sophisticated electronics in ammunition they fire by the thousands and never see again. How do you win a war against an enemy like that?" The American officer didn't answer. There was no need. The proximity fuse stood as its own answer to that question. You don't win against an enemy who can do what seems impossible and do it 22 million times.